In this video I want to explain why I chose to use optimum scaling to perform the principal component analysis. The option OPS, meaning optimum scaling, produced three abstract factors. Now if I simply do a principal component analysis on these data, I can do this by using the Nipal's approach, which will just calculate a simple principal component analysis. When completed, I will have the first 6 abstract factors calculated by this Nipal's algorithm, and when I look at the number of abstract factors that appear to have significant information, I find that there are only 2. So the question is, why are there only 2 abstract factors when I apply PCA directly to the data, and when I perform an optimum scaling, again calculating 6 abstract factors, I end up with 3 abstract factors that look like there's information within them, and the 4th one is noise. When we're trying to analyze data with noise, it's probably worth working with something that we're more familiar with to understand what is happening and why optimum scaling might be different from a direct PCA application. So let's return these data to the raw state and convert the data to spectra. Spectra are probably easier to understand because we do peak fitting on spectra, and when we do peak fitting we use statistics such as the chi-square, and there's a reason why we use the chi-square, and it does relate to the optimum scaling. Here we have an example of a typical spectrum at a pixel, and it really is mostly noise, so it's quite obvious that it's difficult for any routine, any mathematical routine, to distinguish between when we have genuine signal, and there are only 2 points here that I would classify as genuine signal in terms of my understanding, carbon and perhaps some oxygen. But I know there must be other peaks in here, and it's very difficult to pick out a peak that is simply 2 high or 1 high, because this is literally the counts that we have in each one of these data bins. So let's, instead of looking at the spectra pixels, let's sum the columns. So now I have an example of a spectrum that has been obtained by summing spectral pixels in one of the columns of the image. And now it's clear we have carbon and oxygen, and it's also clear that we have some silicon. So the fact that we have added signal together has given us a better understanding of what the spectra ought to be. We've lost spatial information, we've still got noise, and we can still see that the noise here is potentially as significant as these silicon peaks or this oxygen peak. So when you're performing a mathematical operation on data such as these, like PCA, it's understandable why you might lose sight of some of the smaller peaks, and in particular the peak that has been lost, I would suggest, in the set of images when we do the PCA directly on the raw images, is the gold. There's a thin gold wire on the sample, and it is not significant enough when we have noise included in the calculation. So the use of optimum scaling, or any of these other 2 scaling options, is an attempt to reduce the influence of noise on the calculation.